Our today's presentation aims at describing a rapid and simple approach to assess the multiaxial fatigue life in engineering components fabricated by additive manufacturing. The procedure is successfully tested with both structured and unstructured meshes.
This is the agenda. Firstly, the motivation and goals, then a brief overview of the multiaxial fatigue life prediction model. After that, experimental and numerical procedures. Next, results presentation, and finally, some concluding remarks.
Additive manufacturing has received a great deal of attention over the last years because it can meet the current demands of modern industry. In particular, the possibility of creating three-dimensional objects directly from digital files or by the geometric freedom, among others. Within this group of techniques, selective laser melting is currently one of the most popular processes and has been successfully used in different sectors, namely aerospace, automotive, biomedical, and mold industries. Nevertheless, this technique is rather complex. Products are parameter sensitive and are very prone to microstructural heterogeneities, such as unmelted particles, cavities, pores, contaminations, etc. In the presence of cyclic loading, in some cases with a multiaxial nature, the SLM parts are susceptible to fatigue failure. Briefly, multiaxial fatigue models can be organized into stress-based, strain-based, and energy-based approaches. Regarding the notch effect, it is generally accounted for using the theory of critical distances, the strain energy density concept, or fracture mechanics. The most sophisticated models generally require extensive experimental programs and complex computational simulations, which makes the process too expensive and time-consuming in most cases. Our proposal aims to solve these drawbacks. In this study, we propose a simple approach based on a limited number of material constants and a rapid and structured finite element mesh, implemented using a linear elastic framework. As far as the fatigue life prediction model is concerned, the first step is devoted to the material characterization. As shown in this slide, we performed low cycle fatigue tests, high cycle fatigue tests, and fatigue crack growth tests. Low cycle fatigue tests allow the definition of a fatigue damage law relating the SWT parameter with the number of cycles to failure. High cycle fatigue tests and fatigue crack growth tests enable the definition of the material characteristic size. Both the fatigue strength and the stress intensity factor range threshold are evaluated at the same stress ratio of the notched part. The predictive model is based on two premises. 1. Smooth and notched samples accumulate the same damage and have the same lives if the stress-strain histories at the initiation sites are identical. And 2. Fatigue failure occurs when the SWT damage parameter at the initiation site reaches a critical value. The modus operandi consists of calculating an effective value of von Mises stress range at the critical region by applying the theory of critical distances, which is used to estimate a corresponding value of the SWT damage parameter, enabling the calculation of crack initiation life using the fatigue damage law developed in the previous stage. The material utilized in this research is a maraging steel fabricated by selective laser melting. The main mechanical properties as well as the main processing parameters are exhibited at the bottom of the slide. In order to test the model, some experimental work is needed. We have conducted low cycle fatigue tests under fully reversed conditions for strain amplitudes between 1 and 0.2%. High cycle fatigue tests under pulsating loading conditions for maximum stresses between 350 and 150 megapascals, and fatigue crack growth tests under pulsating loading conditions for a maximum remote force of 1.5 kilonewton. All the loading scenarios and the number of specimens tested for each case are represented in the slide. As far as the multiaxial fatigue tests are concerned, the geometry selected was a hollow cylindrical specimen with a transverse hole. The tests were conducted under pulsating loading conditions for 3 different ratios of bending moment to torsion moment. The crack detection was done in situ by means of a high-resolution digital camera. Regarding the numerical procedure, as referred to above, we have developed two independent finite element models. In both cases, it is assumed a linear elastic, isotropic, and homogeneous behavior. The structured mesh created in a parametric manner from 8-node hexahedral elements is presented in this slide. It has an ultrafine ring of elements at the whole region to characterize in detail the stress-strain response at the critical area. The bending moments and torsion moments required to apply the BT ratios were defined by a single force F, positioned at different locations of the prismatic bar connected to the specimen. In addition, we have also created a second model with an unstructured nature using 4-node tetrahedral elements. This approach avoids the time-consuming and laborious tasks associated with the development of parametric meshes, which is much more attractive to the modern industry and particularly in the context of SLM parts. The typical cyclic stress-strain response observed in the low-cycle fatigue tests is presented in Figure 1. Regardless of the strain amplitude, this alloy is characterized by a slight strain softening behavior. However, as shown in Figure 2, the SWT parameter is very stable throughout the entire lifetime. Based on this fact, the fatigue damage law representative for this material was created from the half-life cycles. Here we can see the relationship between the SWT damage parameter, calculated at the half-life cycle, and the number of cycles to failure. In fact, there is a very good correlation between both variables. This relationship can be fitted by a power function. In relation to the high-cycle fatigue tests, as can be seen in the figure, we also found an excellent correlation between the applied stress range and the number of cycles to failure. Here, the fatigue limit stress was defined as the maximum value at which the specimen can endure 2 million cycles, and was equal to 266 megapascals. As far as the stress intensity factor range threshold is concerned, the results obtained from the fatigue crack growth measurements are shown in the figure. Overall, the scatter is relatively low, either at the threshold area or at the Paris regime. The threshold value is equal to 5.2 megapascals root meter. Thus, based on the previous values of the stress intensity factor range threshold and the fatigue limit stress range, we can determine the material characteristic size, A0. Let me show you some results about the multiaxial fatigue campaign. In this slide, we can see the typical crack paths and initiation sites found in the experiments for the different loading scenarios. The fatigue process is characterized by the nucleation of two cracks in diametrically opposite points, whose locations are governed by the BT ratio. The experiments show that the lower the BT ratio, the higher the beta angles. This can be explained by the greater shear stress levels associated with the decreasing BT ratios. Numerical simulations confirm these trends. Fatigue crack initiation sites can be reasonably predicted from the nodes with maximum values of the first principal stress at the whole contour. As shown in the figure, there is a very good correlation between the experimental observations and the predicted locations. In most cases, the errors are lower than 10 degrees. Moreover, the quality of predictions are not much affected by the type of finite element mesh used in the calculations. No significant differences are observed. Regarding the crack angles at the early stage of growth, represented in the figures by alpha, the experimental measurements show that they decrease with increasing values of BT ratio. Not surprisingly, higher BT ratios reduce the predominance of shear stresses, and therefore the crack fronts tend to be closer to mode 1. Angles were successfully predicted by accounting for the first principal direction at the crack initiation site, that is, at the node of the whole contour with maximum value of the first principal stress. The comparison between the experimental observations and the predicted value shows a good correlation. In general, the maximum errors are lower than 5 degrees. The results are not particularly affected by the type of finite element mesh used in the calculations, which is an important outcome. Fracture surfaces, as expected, are also affected by the BT ratio. As we can see, they tend to be flatter for lower levels of shear stress. Examination of the fracture surfaces by scanning electron microscopy suggests that unmelted regions were the main source of crack initiation. It is also clear from the micrographs that fatigue crack initiation sites are located at the whole surface, near the outer diameter of the specimen. These points are close to those predicted by the finite element simulations, white arrows, based on the node with maximum value of the first principal stress, as suggested before. The experimental fatigue lives were determined from the AN curves. Since the fatigue process encompasses the initiation and growth of 2 cracks, 2 AN curves were obtained for each test. In the figure, we can see the curves obtained for the first crack to appear in the specimen. The data, regardless of the bending-torsion ratio and the nominal stress amplitude, were successfully fitted by exponential functions, represented by the dashed lines. Using these curves, we calculated the number of cycles to crack initiation, assuming a crack length equal to the material characteristic size. After the calculation of the experimental lives, we can test the predictive capabilities of the proposed method. The first step, as represented, is the reduction of the multiaxial stress state to an equivalent uniaxial state. This step was done via the equivalent von Mises stress range. As can be seen, there is a very good correlation between the von Mises stress range evaluated at the initiation site, either for the structured or the unstructured meshes. In addition, the values determined in both cases are rather similar. The next step is the computation of an effective value of von Mises stress range at the initiation site. In this work, this was done by applying the line method of the theory of critical distances. The figure compares in a dimensionless form the evolution of the von Mises stress range with the distance from the whole surface along the critical direction for the different BT ratios. The effective value of the von Mises stress range was then used to generate the cyclic stress-strain curves by applying the equivalent strain energy density concept, which were used to compute a representative value of the SWT damage parameter. Once again, the generated hysteresis loops are quite similar, regardless of the mesh type selected in the analysis. We can estimate the multiaxial fatigue lives. This figure compares the predicted values with those determined in the experiments for the different BT ratios. Overall, as can be seen, there is a very good correlation between the data. In addition, predictions are within scatter bands of 2. Finally, it is also clear that the predictive capabilities of both approaches are similar, which is an interesting outcome. Finally, some concluding remarks. 1. Fatigue failure was characterized by the initiation and growth of 2 cracks at diametrically opposite sites around the whole surface. Unmelted regions at the surface and subsurface resulting from insufficient fusion or inadequate penetration were the main cause of fatigue crack initiation. 2. Fatigue crack initiation sites and fatigue crack angles at the early stage of growth were governed by the loading scenario. These variables were successfully predicted from the maximum value of the first principal stress and from the first principal direction at the initiation site, respectively. 3. The proposed fatigue life prediction model, built up with a limited number of material constants and capable of supporting either structured or unstructured meshes, is suitable for industrial applications and particularly to deal with maraging steel parts subjected to proportional multiaxial loading.
Thank you.